Welcome back to Tech Command Investing, the podcast where space, defense, and cybersecurity collide with the future of investing. I'm Alain Gavin, your host, and a long-time investor in deep tech and dual-use innovation. Today's episode takes us from the thin air of mountaintop observatories to the fiber-like highways of tomorrow's space networks. My guest is Jean-Edouard Communal, co-founder and CEO of Miratlas, a company whose mission is simple but transformative. Without their atmospheric data, laser satellites in low Earth orbit simply cannot connect to the ground. Their measurements and forecasts are fast becoming the invisible foundation for secure, high-capacity optical communications. At this point, I'd like to point out that Miratlas was one of our first investments made in Carista's Tech One fund, also known as Cosmic Capital. In this episode, we'll explore how Miratlas is redefining what's possible for global telecoms and defense, why sovereignty in the optical domain matters, and how dual-use innovation is once again changing the rules of conflict and connectivity. Well, let's get into it. Jean-Edouard, what was the aha moment that made you realize the ground, not the satellites, was the bottleneck, and what's the Mark and Sky Monitor stack in a sentence?
In a sentence, well, first off, hello, Alain. Thank you very much for having me on the podcast. It's a real honor and pleasure to be there. The haha moment. I can tell you exactly where was the haha moment. It was at Photonics West, sometime around 2015, so in San Francisco. And I had assisted to a workshop on free space optical communication, which still happens in Photonics West every year. And at the time, I was in a different career path, and I was like, "Oh, this is very cool and very interesting." It was the premises of the bleeding edge research people from JPL and doing free space optical communication and developing the technology for research. And I was like, "Wow, this is groundbreaking." And at the time, SpaceX was starting to launch and reusable rockets, and they were trying to stick the landing. And I think in 2015, that's exactly when they stuck the landing. And I was like, this is going to be a huge change. The next step is going to be optical communication, because if you take the conquest of the West in the US, there were two things. You had the trains, which to me for space is the reusable rockets, and you had the telegraph, and that's free space optical communication. And if you can get these two things, then you have infrastructure in space, and it's really transformative for the telecom industry back here on Earth. So that was the haha moment. And we realized that the benefits of optical communications are great. The capacity, the point-to-point communication, very very difficult, if not impossible, to intercept. And with my background as a physicist, I was like, oh, these guys are going to have a problem with the propagation medium, because for terrestrial communication, you're in a fiber optic. It's the best medium for that. In vacuum in space, it's even better because you go 30% faster, you go in a straight line. So it's a no-brainer. Once you figure out the pointing acquisition and tracking, there's no issue there. The trick is going to go with laser propagation for the atmospherics, because you have all sorts of issues. I worked a lot in the astronomy market, and the astronomers, they have no choice. If they want to look at the sky, the stars, and have good measurements, they need to be on the best place on Earth, in Chile, in Hawaii, thin atmosphere, no clouds, no turbulence, and they spent decades to select the right site. Obviously, you can do that with telecom, but you are going to have all the problems of astronomers with cloud cover, with turbulence, with absorption, with the added problems that you cannot be on the best location on Earth, and that it needs to work 24/7 because it's going to be telecom. So you cannot just look at the stars and say, oh, tonight is great, I'm going to have some great results, and I won't work during the day, or next day is going to be cloudy, it won't work. It needs to work 24/7, and that's the real challenge.
We'll get into that in the demo later on in the podcast around selecting those sites. But Miratlas has described its mission as unveiling the sky. And I think that's quite revealing, and that says how you can resolve the issue. And so how did those early deployments prove this was a commercial problem, not just a scientific curiosity for
Yeah.
astronomers or others? Yeah.
Yeah. The trick was to unveil the sky. That was kind of a three steps approach from the get go. First off, you need to measure cloud cover and turbulence. And typically, cloud cover was measuring during the day by people doing photovoltaic, and turbulence was measuring at night by people doing astronomies. So it started with an instrument which we call the Sky Monitor now, and that was designed to be telecom grade, easy to deploy, low footprint, low power consumption, just passive optical sensing to gather all the data that would be required for laser communication. And it was basically all the instrument developed by astronomers for decades, but really on a niche market and on a very custom research based stuff. So that was the first thing, the instrumentation. The second thing was, oh, that's great. Once you have this instrument, you need a network. You need a network of instrument because telecom is all about network. So you need to connect all these point-to-point locations on the ground to the constellation in space. So you need a network of instrument to be able to gather the database that you need. And of course, once you have this great atmospheric database, the first thing people ask you when you talk about the weather is, is it going to rain tomorrow? Or what is going to be like today? So it's
Cloud cover
forecasting.
or whatever, right?
Yeah. So it becomes a more fancy version of that, including cloud cover and turbulence. And can you forecast these parameters? Can you translate them in a link budget first? Are they to make them relevant to operators? And second, can you forecast them so you can make link before you break them, and you can optimize the whole network operation according to weather? So it's like instrumentation, database, and then machine learning for data translation into actionable information and forecasting. So that was from the get-go. That was the vision. That was the idea, and that's how you unveil the sky.
Well, we'll get into the detail later on, but in the meantime, why this matters for investors. You heard investors often ask, why not stick with RF, radio frequency? Can you explain why spectrum limits and
Yeah.
bandwidth ceilings make optical inevitable? And I think it'll become clear when you look at the figure one, I
Yeah.
think it's, yeah.
Yeah, as part of a haha moment was like, okay, there's a technical solution and we can achieve that. It's within reach. And the second part of the haha was there's a huge market for this, like massive. It's basically down to the digital divide, where 1/3 of the world population still doesn't have any connectivity whatsoever, no internet access, nothing. We're not talking about broadband versus slow band. We're talking about nothing at all. And that's despite the fact that the telecom market is a huge $2 trillion market. But despite that, you still have 1/3 of the population which is unconnected. And that's basically down to one thing, is that the terrestrial telecommunication infrastructure is costly, it's fragile, and it only makes economical sense to deploy this in densely populated areas, which is where you make the most money. And that makes complete sense. Now, with SATCOM and with reusable rockets bringing down the price to orbit, the price of satellites to orbit, you actually deploy a telecom infrastructure in space. And the superpower of satellite communication is that it gives you global coverage, true global coverage. Its limitation, though, is radio. And in the telecom world, radio is used for end users. It's low capacity. Even if you're talking about a few hundred megabytes, which is great for you, it's nothing compared to the terabytes and terabytes of data that fiber optics is capable of. So radio is a technology which is used for niche market, for edge of the network. So it's a low capacity stuff. So as long as Satcom was using only radio to do both its core networking and its edge networking, it was very limited in market size and reach and very costly. So the trick is, how can you make Satcom a true telecom players? And it's actually very, very simple, because you think of telecom, you need three things. The first thing is low latency. And that's provided to you by using LEO mega constellation instead of GEO. Basically, you don't need to go to 36,000 kilometers. You're only going up to 500 kilometers and back down. So the ping pong is the time of flight is just shorter. So that gives you the low latency. That's one. That's what you need for networking. The second one is high capacity. And that's where you need optics, because optics gives you 1,000 times more capacity than radio. That's just physics. The wavelength is shorter. You pack more information into the same wavelength. So that's high capacity, and that comes from using optics. Now, the last thing you need for core networking is reliability. And that's where you have the problem, because radio is very reliable, but it's low capacity. Optics is high capacity, but through the atmospherics, is become really unreliable. So that's the trick, and that's really Miratlas' mission, is how do you unveil the sky to make sure that it's not a problem anymore, and you can ensure reliable optical communication between the existing terrestrial infrastructure, which is developed in high population density area, to go up to space, which will then cover the whole world economically, including the low populated area. And that's pretty much it. How do you make high reliability optical communication to make Satcom into a true telecom player? And that's the mission of Miratlas.
It's basically about moving from what was the niche for RF, and I did notice that the satellite companies in the past were quite small, to telecoms, which is a multi-trillion market. Yeah,
Yes,
exactly.
absolutely. And I would say, if you want to bring high reliability to optical communication, you need a few things. You're talking about 5 nines reliability. And according to cloud cover and turbulence, you will need to use different techniques, different strategy to mitigate the atmospherics. The first one, which is very obvious, is site diversity. If you have a cloud over your head, you want to link to the next point of the network, of the terrestrial network, which has a clear sky. So you need geographical site diversity. The second thing is more relevant to astronomers. They are more familiar with this, is turbulence. When you look at the star, it twinkles. That's because of turbulence, and that affects the capacity as well. So you need to use some sort of adaptive optics technique to mitigate that. But that's not enough. Even with the best adaptive optics system, and these things are costly, you still have some deep fades where the signal will drop. And this you mitigate by encoding, where you spread the message in time. And also when you have a deep fade, the rest of the information will be reconstructed through the encoding algorithm. But that increases latency. So you want to use it, in a smart way as
Yeah, exactly.
as much as possible. And the final one is network routing, where you would optimize the links between the network, be it optics, be it radio, be it whatever is available on the shortest distance and the lowest latency, while maintaining the capacity. It's basically overall network routing, which will sing and dance according to weather conditions. So it's all driven by weather. All these mitigation techniques are all driven by weather.
Mm-hmm. And then going on to what Gartner places optical to orbit. They say that that's going to be, the adoption window for that is 3 to 6 years. What milestones over the next 24 months do you think will prove that shift? I think we can refer to figure 2 for listeners. It will be in the download as well. The 1 trillion annual market to bridge the digital divide, and which is what you just talked about the third not still being connected.
Yes. Well, I think it depends on the different types of application. The first historical SATCOM, the most commonly used SATCOM application is broadcast with geo satellites. And you can replace the radio feeder link by a network of optical feeder link. For this, you need about like 10-ish ground side to cover a continent and beam up to your geo satellite. The second one, when you start to go into Earth observation and optical downlink, for this you will need like hundreds of sites. And when you go into full satcom to telecom, then you talk about thousands of sites. The order of magnitude is thousands, 10,000, things like that. Simple fact, it's kind of the piano tuning problem. You have tens of thousands of satellites for these mega constellations. The links are point to point. So you will need to link to the ground with an equivalent number of sites. And this is about also the same number of sites that you have in terrestrial infrastructure. If you look at the internet exchange point, if you look at the data center, if you look at the cable landing site, place where you have really strong terrestrial infrastructure, it's about the same number. The trick is, which one do you start first? Which one are the low-hanging fruits, which give you the highest capacity? What is the smallest network you can deploy on the ground on Earth? And it needs to be all over Earth because the constellations are flat. The satellites are all over. With the optimal site diversity to ensure this reliability of the link. So you're looking at weather decorrelation as well. It's complicated.
Yeah. So what do you think will be the thing that moves it from this 3 to 6 year window of adoption to maybe a shorter time span, maybe 24 months? I mean, is it the infrastructure on the ground or?
My bet is infrastructure on the ground, yes, because you always have this kind of chicken and egg of do you build the ground segment first or do you build the constellation first? And people in the space area are always about putting satellite up there. And the the ground will follow. The logistics will follow. But people in the telecom business, they build this business case for like 10, 20 years or something like that. They lay a fiber optic cable, a subsea cable. They construct data center. They make sure they have the power supply first. They have the cooling. They have all this infrastructure in place. And then they will get the money in a regular fashion. So it's basically, I think it's the infrastructure comes from the ground because that's the costly one. The data centers locations are known, and they're investing a lot with all the cloud services, not to mention AI. So it's really about, it's easier to put an optical ground station on the terrestrial infrastructure than to put a data center on top of the mountain. So I think the move will come from the ground, and the ground network is also very standardized. All the telecom networks are standardized, the protocols are standardized. Not so with SATCOM yet. So the standardization and the leverage will come from the ground, and the reach, the final reach, and the access to the customer, to the market will come from space.
Mm-hmm. And then, of course, I'd love to know in simple terms if you could describe or walk us through a real example where Miratlas data increases uptime and therefore revenue for the operator and these telecoms operators.
That's a very good question. The first thing is site selection. You want to look at places of your existing ground segment where you have good atmospheric conditions, but not only that, also where you have decorrelated weather conditions from one to the next. And you're looking at the smallest possible network to get you to the reliability of the connectivity that you're looking for. That's the first thing. The second thing is, according to the cloud cover and turbulence measurements we get, is specify the optical ground station the specification, performance. If you have strong turbulence, you will need fancier and more performant adaptive optics, which will be more expensive. So you try to minimize the cost of each ground station according to weather. So we can draft the specification of the optical ground station. And the final step is to try to optimize the operation of each site by carefully looking at the cloud cover and the orbital parameters to be able to say, okay, You may have 50% cloud cover in this location, but you can still address all these orbits, all these satellites, and ensure the connectivity, which is what is bringing you money. If you have equipment on the ground which is not being used, then you're wasting money. So you really try to optimize the uptime of each single site, each single optical ground station, and then the network optimization will take care of itself. It'll be part of the network routing, which we don't do.
So, Edouard, scaling reality check. We have talked about thousands to tens of thousands of ground sites in the long run. What's the realistic phase one density to make a national optical downlink viable? And of course, then who pays for it first? Yeah.
Yeah, it's a very good question. I'm not sure I have the answer, to be honest with you. It's kind of orders of magnitudes and rules of thumbs. For a network to be reliable, you need site diversity, especially with weather. And it really depends on the use case. A geo satellite will see a continent. So as long as you have like a dozen or so sites, that will make sure that you've got your 99 point whatever availability. But a geo satellite has a very large field of view. For a LEO constellation, the story is different. You'll need like hundreds of sites because the coverage is global, and you have many more satellites, and each of
Per
them see a
country, you mean, yeah? Hundreds of
yeah,
sites per country, yeah.
hundreds of yeah, pretty much, yeah, because each satellite will have a much smaller field of view, which is part of the magic with how we can address this population. But the lower field of view, the satellite being closer to the Earth has a lower field of view, so you
At
need
a higher
more
latency, yeah? So lower latencyy, which is what we're
lower.
trying to achieve, yeah.
Yeah, yeah, that's exactly it. So you're looking at hundreds of sites for LEO to start with on the size of a continent. I don't think the size of a country is large enough in terms of spatial diversity. You really need to think in terms of continent, or even better, on a global scale. Because even if you're going to address a small constellation, um, you need to have your station, your ground station throughout the world, which is what you can see in Earth observation. You have ground station pretty much all over the world. That's what happens in RF, and it'll be even more critical for optical communications.
Mm.
And if you want to check on figure 3 for people not watching this, so that's the ground network. That's the infrastructure of subsea cable landing sites, internet exchange points. And these are the places on Earth you want to connect to space most efficiently through weather.
And now getting really into the meat of it, then your unique product and the technology edge that you have, you combine like real world measurements with models to forecast conditions. What
Mhm.
makes those forecasts actionable, not just interesting?
That's a great question. It's it's down to the precision of the data and the parameters that you measure. I'm sure you've seen Google has tried some machine learning on forecasting, weather forecasting, with great results. And that's because, contrary to large language models, you're using atmospheric data, which is rooted in physics. AI is really good at this. Now, the trick is, if you use, it's about spatial resolution. You need high resolution data, very local data on the exact location where you're going to put your optical ground station or your nodes. So high precision, continuous data, and you also need to include the turbulence, which nobody else has measured. So we combine the two, like maybe 100-fold more precision on the data, both temporal,
Mm.
including cloud cover and turbulence, some parameters that nobody else measures, all of that rooted in physics. And we also do our own modeling of turbulence based on historical weather data. So we have a very strong data set of synthetic data. That's the term when you have both real measured data and model data. So we have a very large data set of synthetic data, which is unique and allows us to model what would be the perfect network for this very demanding application. if you look at figure 4, you'll see our instrument, which we call the Sky Monitor, which we've designed to measure cloud cover and turbulence by night and by day with really high resolution. And that's what the key is. Turbulence, nobody else measured before us at the scale with the continuity that we provide. And cloud cover, we have also very high resolution measurements. So that's part of the real measured data. The other part is of the atmospheric database is modeling of the turbulence. That's part 2. If you look at figure 4, part 1 is the instrument. Part 2 of the atmospheric database includes bleeding edge turbulence modeling on a global scale. And this synthetic data sets forms the basis for the training of machine learning algorithm, which is the third part of the of our proposal, where we do both the cloud segmentation to really recognize the clouds, where is the visibility to the satellite is going to be good or not. Translate the atmospheric parameters from turbulence, absorption, all of that into a link budget, which will be actionable for the telecom operators. Translate the cloud map into which direction can the OGS point and address which orbit, which satellite, and that's actionable data for the operators. And the next step is, as soon as you have this data, people are going to ask you, what is it going to be like in 15 minutes, in half an hour? So the final part of these equations, once you've translated all these parameters into actionable data, is to forecast them with as good a confidence and as long a time margin as possible, so you can really help to optimize the network routing on a global scale.
Mm-hmm. Yeah, you've now shifted from hardware to a data service model. What does a client actually get from you day to day? So what does he see on the screen, or how does he get actionable data?
So in practice, the instrument that you see in figure 4 on the left hand side, the instrument, you can see on figure 5 in situ on that's actually a ground station from our friends at Skylab in Western Australia with SSC. And you can see that on the size of the container, this is a standard shipping container. And our instrument would be on the top right of the container. You'll have the tracking mount, because being in the southern hemisphere, you cannot see Polaris, so you have to use different stars. You have the weather station, you have the Sky Monitor itself. It's all contained and designed to be dropped very easily and attached to the top of the container. And you can get a sense of the scale compared to an optical ground station with the telescope and the shelter and everything. So it's designed to work in coordination with the ground station to help its operation, but it also is designed to be dropped before you selected the site for the ground station. In this particular case in Western Australia, it's fairly flat. The weather is fairly steady. So 100 meters to the left or to the right wouldn't make a big difference, but on a global scale, it makes a lot of a difference.
Mm-hmm. And so if you had 60 seconds to convince a CTO or skeptical CTO, what one output or chart would you show them?
Would you spend like $1 million on an optical ground station if you don't know the return on investment and the operations? You really need to be able to characterize, to measure twice before you cut once. So before you deploy your asset, your ground segment network, you need to model it, to game it, to make sure that you A, going to deploy it efficiently, B, quickly, and C, that you'll have the operability that you're looking for and the return on investment you're looking for.
Great. I mean, before we get into a live demo, which I think people are going to wait for, I just wanted to bring in the defense and sovereignty aspect into this. Defense is often the first adopter. Can you paint a vignette where an optical link enabled by your forecasts makes the difference in the contested environment?
There's two aspects which are interesting to the military for optical communication. The first one is you don't need a lot of capacity. The point-to-point connectivity makes it very hard to intercept. So it is more an aspect of stealth, which is very interesting there. You can have high capacity. I mean, even if you have 1 gigabits or 10 gigabits, which is fairly easy without adaptive optics, with optical communication, that's a lot of data for a single operator or asset on the ground. That's a lot of data, but it's also going to be extremely difficult to detect. And you're not like when you're broadcasting radio, you're not saying, "Hey, yeah, look at me, here I am," and yeah, some nasty stuff is
Yeah,
going to
because
come
it
your
goes
way.
for a broader field, whereas optical is
Yeah,
right focused on a specific area.
yeah. The laser communications are point to point and extreme. So you're not difficult to intercept and difficult to trace. That's the two things. Some people say that it's also resistant to jamming, but technically a cloud is jamming. So if you have a contested environment in terms of RF jamming, of course,
Yeah.
optical communication is not going to be sensitive to that, but you're going to be sensitive to a smoke screen or a cloud. That is essentially jamming for optical as well. So in terms of defense, I think it's more the stealthy and discreet aspect of the communication, which is very interesting. And that's on the edge. But of course, like any military base, when you project forces around the world, people want their entertainment. They want their watch their videos. They want to play video games. So you need broad capacity. But that goes back more to like a classic telecom business
Yeah.
model. But if you put in place the infrastructure on the ground to address your assets, be it on the theater of operation or just from a logistics point of view, that means that you have complete control of the infrastructure from the ground, from the satellites, back to your assets on the ground. So it's a much more vertically integrated solution for the military as well.
Hmm. And looking beyond the comms, obviously you want your soldiers to be happy in their free time. Um, but your ground stations are effectively sky watchers. Yeah, what potential military or dual use application might there be, from subspace situational awareness to missile warning?
Uh, yeah, to be honest, not so much because uh, the only common ground is that using a telescope, but the payload, the detector at the back, is very very different. For optical communication, you're looking at a single point with fiber optics and whatnot. You don't have a camera. You're not doing SSA with optical communication equipment. However, the locations is could be very interesting for both these applications, and the technology will be very similar as well.
Yeah. Okay. Well, let's now dive in, I think, to a demo. And for YouTube viewers, we'll bring the dashboard live on the screen. For Spotify, Apple, and Audible listeners, Jean-Edouard will describe what he's showing: cloud cover, turbulence, clear sky paths, so you can visualize it without the visuals. But obviously, it'd be great if you looked at the YouTube to see this live happening on the screen.
So here what we have are statistical data for the past 5 years, average night and day of cloud cover. So if you make the site transparent where the cloud cover is less than 50%, then you can immediately see the areas on the ground on the planet where potentially will be interesting for optical communication because you have low cloud cover. So obviously Australia is a good place. South Africa, obviously all of North Africa with Sahara, Saudi, uh, all the bands around the Mediterranean area as well. South America, west of the US, Mexico, all these places. All these places are good for cloud cover. Okay, but
Absolutely.
as we know, cloud cover only tells half of the issue. If you look at the R naught, which is one key measurement for the turbulence, and you apply this similar kind of setting where half of the threshold is low, so you can here see the places where turbulence is interesting, and turbulence is good in
But not
very few
always. Yeah.
places. When you have low cloud cover and a lot of heat, that's usually where you have a lot of turbulence. So you can see that Australia is completely in the red. The Sahara Desert, we used to look good for cloud cover, is not so good anymore. But
Mm.
you still have places which are interesting. Like, for example, in Chile, you realize that's exactly where the astronomers put their telescope, because you have both low turbulence and low cloud cover. Obviously, Hawaii is also very good.
Mm-hmm.
So it allows you to paint a much more complete picture of both cloud cover and turbulence, and one might not go with the other. In fact, it's usually quite the opposite. And then you want to make the link, where can you see through these conditions? Where is the ground infrastructure that is interesting to you? So we can superimpose the submarine cable, the cable landing site, the internet exchange point, all the places. I'm going to take off the subsea cable, so just so we can see. All the points that you can now see on the screen are points of infrastructure. And you want to link those points of infrastructure according to the weather condition to space. So it's really how selecting where do you see the ground here would be interesting locations. But this is an average over 5 years and night and day. Now, if you look at the average during daytime, obviously you have a lot more turbulence because of the sun heat, and this is all mapped out, daytime throughout, no matter where you are on Earth. And nighttime, obviously the turbulence is much easier as well. So you're going to want to look around at proper around the world networks, so you can always be in the right position and right location at the right time of the day. Similarly, if you look at seasonal variations between Q1, Q2, Q3, and Q4, you see how it will change. The seasonal variations become important. So not only do you have variations during the day, you have seasonal variations as well. So yeah, weather is complicated. So you're always looking at the right path on the network, the right window, and that window is always changing, changing with the date, time of the day, changing with the seasons, and changing with local weather parameters. Uh, so so that's what helps us guide our customer towards the optimal network throughout the world. And then what we do is we compare to our sky monitor networks. So the black dots here are where we actually have instruments, and we will anchor the modeling into real data. So the real data will feed into our modeling and forecasting algorithm to try to match the reality as close as possible.
You see the one down there in maybe if you zoom into one in Australia that we
Yes.
just saw before, and
Yeah.
see why that one's well located, because it's out of turbulence, I think, or
Yeah,
so.
it's out of cloud cover. Turbulence. No, it's a bit. It's really mostly due to the heat. If you look at the between daytime, here this was the only daytime
I see. It's
versus
on the edge, yeah.
versus nighttime. You can see that nighttime it's pretty good. Daytime the heat will be pretty bad, but you're not so as you're close to the coast, you get a benefit from this. So this is actually a pretty neat location. It's like everything. It's a matter of compromise. And it's also where do you already have existing infrastructure which you can leverage easily. Uh, yeah,
Because you see the
that's
subsea cables are coming in through there, right? If you
yes. You can look at the subsea cable,
Yeah, they're coming in down there. That's why it's
landing in Perth. And you can zoom in into the Mediterranean, which is very well littered with subsea cables. See, Marseille is quite a hub of subsea cable and data center, and the conditions are quite nice. You have Cyprus, you have Crete. If you look at the Middle East as well, there's a lot of subsea cable and cable landing sites, and the conditions and this is daytime, so where you would have a lot of turbulence. Nighttime will be a little bit easier on the telescopes. So that allows you to look for the locations which would be really interesting, but the spatial and temporal resolution of these models are not enough to be able to guide the actual day-to-day operation. For that, you need the sky monitor on site to provide you with a precise and complete data set.
So how would a customer then, or how would you advise a customer to put locations? Give us an example of one where you showed them where the location was using this data that you've gathered.
So what we'll do here, that would give us, it doesn't, modeling is not enough to tell you if a site is going to be good. It's enough to tell you if a site is going to be worth checking out.
Yeah.
And then we will put a sky monitor there, and we will get the same data you can see on the screen here, but with much higher precision. You will see, like, for example, what you have on, if I can skip on figure 7, where you have the all sky images of the cloud. We do a pattern recognition of the cloud cover with both the thermal and visible camera. And thanks to this and knowing the orbital parameters of the satellite, you know which paths are going to be clear to enable a connection. It's a little bit easier for the geo satellite because they're apparently not moving in the sky, so you know exactly where the satellite is and where the cloud is moving in or moving out or disappearing. So we optimize the operations in real time with this, and we will. This is for the cloud cover, which is a bit more visual. I think it says 6 is the static view of the live demo, where you can
Yes.
select the side combination, which will be complementary from one to each other.
Anything else that we can learn from this and how it'd be used compellingly for a customer?
That's pretty much it. I mean, it's fairly
Okay.
simple. You just look up and
Okay.
and see what the weather's like, and extrapolate from. Essentially, we're using the sun and the stars as reference source. You know, if you don't see the star, and then there's a cloud. If the star is wiggling too much, then you have a lot of turbulence, and you're going to lose on a yeah, you lose on capacity of your laser link. So it's a very elegant passive sensing method to be able to select the location before you go into purchasing an optical ground station and a network of optical ground station.
Well, for example, I see one there in France. How was that selected, that location there in France?
Oh, two things. We're based in Aix-en-Provence, so it's convenience. Like a
Yeah.
lot of manufacturers, you know, if you're a manufacturer of optical ground station, usually you put it on your doorstep or on an observatory site because you're not looking at telecom applications yet. You want to test it as much as possible. But for operators, it's all about the network. You want to, it's like a network of supercharger. You don't need just one, you need a network of them to be able to travel. So you need to think in terms of your network. How are you going to deploy your network? So for us, we have our own location in Pertuis. We have our testing site at the Observatory of Haute-Provence, where the Onera is going to have an optical ground station. We have different sites where people already are also testing ground stations, so we can correlate our atmospheric data to the link budget that they're actually establishing with satellites.
But I see that some of them have quite some cloud cover on them. Is that because they're
Yeah, it's the thresholding. I mean, you're always going to have a cover. These are average cloud cover throughout
Mhm.
the year, and
I see
you're
there it's
always
much
going to have.
better, yeah.
Yeah, yeah. It's just how you display the conditions and how for example, let's say your ground station will give you would be available when you have 60% less than 60% ground cover, cloud cover. All these area of France will be available then. But if you're a little bit more restrictive on the cloud cover, then you're really talking about around the Mediterranean. And again, you have to think that these conditions are changing all the time. So it goes back to what we're showing on figure 7. How do
Mm.
you really optimize each and every optical ground station according to their own conditions?
Yeah, well, thank you for that. I think that was very informative and shows, just how much data is involved in collecting. I think you have 50 odd ground stations. Is that right?
Going on 60 now. I'm going on 60, yeah.
More
But
than 60. So
going
that's great. And yeah, maybe looking ahead, he says Hydron
Mhm.
and private actors like Kepler and others are deploying optical ground backbones. How do proliferated optical ground stations networks change where you place sensors and how customers buy your data?
Our customers are we have essentially three types of customers. We have research institute, which are on the bleeding edge, or space agency, which are on the bleeding edge of the technology. But this is kind of like the run of the mill. The next step are the equipment manufacturer, like the people that actually manufacture the OGS to telecommunication grade, like a standard off-the-shelf product to point and establish the link with satellites. But the final customers are the operators that are going to purchase a network of these OGS. And I'm sure you've heard in the news when Starlink purchased the spectrum from EchoStar for $17 billion. That's because the spectrum is very restricted. So they invested $17 billion to be able to have the access to the end user. And that's a critical resource. But if they're going to spend that money for the end user, you have to realize that you have to spend an equivalent amount of money for the back end, for things to work. So of course you spend the money you invest in what brings you money first, but eventually you'll need to make sure that everything works, because if you have subscriber and the connectivity doesn't work, like we've seen this morning,
Yeah.
then you're not going to have customers for a very long time. So you need to invest in the optical ground segments that would support the operation and the link between your space assets and your terrestrial assets. Not only that, because we've seen that spectrum is very expensive. So if you're using half your spectrum to address your customer and half your spectrum for the backhauling for your own means, then you've paid for it twice and you're only getting half the money.
Oh.
So as much as you can transfer the backhauling to optical, that first off, that increases your capacity tenfold, hundredfold. That's one thing. And second, that spectrum can be reused and addressed for paying customers who are not going to deploy an optical ground station, who need their connectivity to work no matter what the weather conditions. So you want to keep the radio spectrum for paying customers, and you want to transfer as much of the backhaul as possible in optical, where you don't pay a license fee. So that makes the cost of the technology very, very cheap, because you've saved 17 billion just on not licensing the spectrum. So yeah, that's the play. You need to provide both the back end, the backhauling in optics, and to save your money and your spectrum for paying customers.
Okay. Now let's look at something quite different and looking ahead as well. Looking ahead to drones. Yeah, what's the roadmap for? You said beforehand that laser is unjammable. Of course, if you have tile cover, that's a problem. But could you have unjammable drones communications via optical links? And
Uh,
and which hurdles or technology hurdles need to fall first? Is it
uh,
terminals,
I,
pointing, accuracy, deployable?
I think it's a case of Back to the Future, because you already have like missiles and drones that were using fiber optics back in the day to link to the drone
Yeah.
or to the missile. So that was optical communication, but it was just using a fiber optic.
Right.
Uh, so if you can do that with free space optical communication, meaning pointing a telescope, and you don't need a lot of capacity there. So it's really a question of pointing acquisition and tracking, and make sure that the weather conditions are good enough so you can do that. Then yeah, of course, it's usually beneficial, because it makes it a lot more flexible than the fiber optics.
Yeah, of course. Yeah, it becomes, yeah, as I say, impossible to jam. Yeah.
Yeah.
And then finally, on the future, or back to the future, beyond drones, which other technologies, AI, quantum, or edge computing, stand to benefit from, or the
Ooh,
most from optical to orbit connectivity?
that's a good question. Hmm. Uh, all of them. All of them. Quantum communication, you're referring to quantum key distribution or
Yeah.
quantum communication. For this, you need to send entangled photons through the atmospherics. And that's a big one for both security of communication, because your quantum key cannot be intercepted without you knowing so. That links to quantum computing as well, because one step beyond quantum communication is quantum key distribution is quantum communication, where you can link quantum computer from one together and multiply their processing capacity. AI, we're both using AI already, but you see the huge the large data sets that you need to transfer to train models will also benefit from this, and also putting data center on the edge, in places where you can be very disconnected from the rest of the network, geographically,
Or
like
even
on an island.
data centers in space, yeah, is what they're talking about.
Yes, I mean, you basically want two things. You want power to power the GPU, and you want cooling to cool the GPU. So wherever you get power and cooling the cheapest is where you want to get your connectivity to send your data set and retrieve your process data. So if it's on an island somewhere because you have cheap solar and cheap cooling, or is it in space? Yeah.
Cheap cooling there, it's freezing, yeah.
Yeah. Well, it needs to be radiated cooling. It needs to be radiated cooling. So it's
Yeah,
not.
definitely, yeah. Well, final reflections, really. If you could recommend 1 to 3 books to help investors and policymakers understand your work, what would they be?
Interesting. I have one right there. I don't know if you can see it. So it's in French. It's How the World Works. I got it in French, so my friends could so I could learn it to my French friends. How the world really works from Vaclav Smil, which I thought was really interesting in terms of the metrics, the energy, the concrete, the fertilizer, all the stuff our society relies on, and which is basic raw materials or industry patterns.
Mm.
And I think it's very relevant to what we're trying to achieve at Miratlas, because connectivity is, we are having this podcast in distance, and connectivity problems aside, we don't need to travel. That's a really low cost in terms of energy to do this, because only the photons are traveling, not us physically. So it's a time saver, it's an energy saver. So the connectivity is going to be, it's a real asset for the society. And SATCOM combined with optical communication gives you the broad coverage at a very low cost, both in terms of material, in terms of energy, and gives everybody access. So I think it's a huge, if we can lift this limiting factor and bring the rest of humanity and industry and commerce and education and health through this sharing of information for a very cheap price, both in terms of materials and cost, then yeah, that's a huge limitation we've lifted on the world.
Okay, perfect. Well, with that, thank you very much, Jean-Edouard, and good luck with Miratlas and getting your thoughts to the world.
Thank you very much, and I appreciate the opportunity. It was a pleasure talking to you, and until next time.
Until next time, yeah. Thank you. Bye-bye.
Thank you so much.
If you're an LP interested in learning about space tech, defense tech, and security, including cybersecurity investment opportunities, let's chat.